Hi everyone, welcome to goclasses. In this lecture, we will continue our discussion of relations closures. In this lecture, we will study equivalence closure of a relation. We have already studied what is relation closures concept, what is reflexive closure, what is symmetric closure, transitive closure, all the concepts, practice, gate previous year questions, and also proofs. Basically, everything we have studied in the previous lectures. In this lecture, our main topic is equivalence closure, also commutativity of relations closures. When can I say that two closures, two relations closures are commutative? Okay, so this is our main topic of discussion for this lecture. Let me tell you that on YouTube you can search Go Classes Discrete Mathematics and you will find this playlist Discrete Mathematics Gate PYQs, Compact Lectures, Practice Questions, and Revision playlist. Okay, so in this playlist, you will find Discrete Mathematics, all the compact lectures, Gate previous year questions, discussion, practice questions, and revision playlist, revision lectures. Okay, so you can search Go Classes Discrete Mathematics on YouTube. Now, let's see what is the content for this lecture. So, in this lecture, we will study commutativity of various closures. When can I say two different type of closures are commutative or not? Next, equivalence closure of relations. Next, this third topic, this is optional, means for the gate exam it is not required. Basically, we will understand the proof. We will see the proof of a theorem that we have seen in the previous lecture. In the previous lecture, we have discussed power of adjacency matrix of a relation. Okay, the concept powers of adjacency matrix of a relation. So this concept we have discussed, a theorem we have seen. Now in this lecture we will see the proof of it. Okay, so this is optional for the gate exam. You can skip it. It is not required for the gate exam, so I am keeping it optional. Okay, but these are very easy topics and very small topics. So let's start. Let's study commutativity of various closures. When can I say two different type of closures are commutative or not? What is the meaning of commutative? Let me tell you. Commutative basically means that you can do them in any order and the result will be same. Okay, let me tell you. Commutativity is like this. Whether you do A has B or whether you do B has A, both are same. Okay. So in this situation, we say that has is commutative. Okay. Let me tell you, commutative basically simply means that you can do two things in any order. For example, you can do A hash B or you can do B hash A. Then if the result is always same, then we will say that hash is commutative. For example, you already know that A plus B is equal to B plus A. So addition is commutative. But you already know that A minus B, it may not be same as B minus A. So subtraction is not commutative. Okay, addition is commutative, subtraction is not commutative. Similarly, multiplication is commutative and division is not commutative. Okay, we already know that A multiplied by B, that is always same as B multiplied by A. So multiplication is commutative, but remember, division, that means A divided by B and B divided by A, they may not be same. Okay, correct. So I can say that multiplication comma addition are commutative, but subtraction and division, they are not commutative. So I hope you understood the meaning of commutative. So now we are discussing commutativity of various closures. So commutative simply means the result will be same if you do two things in any order. Okay, that is the meaning of commutative, but you understood the idea. Okay, order of operations doesn't matter. Basically, I can say that order of operations doesn't doesn't matter, the result will be same. Okay, so now let's see, when can I say two different type of closures are commutative or not? Okay, in the previous lectures we have already seen that reflexive closure and symmetric closure, they are commutative. Do you remember? In the previous lectures we have already seen with proof, the proof also we have seen that reflexive closure and symmetric closure, they are commutative. What it means? It means that for any relation R, if you first find the reflexive closure, then you find the symmetric closure, or if you first find the symmetric closure, then you find the reflexive closure, both the result will be same. Okay, so you can see for any relation R, the following is always, the following are always same. Okay, the following are always same. The following are always same means for the relation R, first you find the reflexive closure, and then on top of that you find the symmetric closure. Or for the relation R, you first find the symmetric closure, then on top of that you find the reflexive closure. Then remember, the result for both of these will always be same. Okay, so I can say that reflexive closure and symmetric closure, they are commutative. You can perform them in any order, the result will be same. Okay, very simple. Now let me ask you a question. Can I say transitive closure and reflexive closure, they are also commutative? Can I say that for a relation R, can I say that both of these two operations are always same? They will always produce the same result. Means for the relation R, first you find the reflexive closure, then on top of that you find the transitive closure. Or for the relation R, first you find the transitive closure, then on top of that you find the reflexive closure. Can I say that these two will always produce the same result? Can I say these two are always same for any relation R? What do you think? Can I say transitive and reflexive closure, can I say they are commutative? Let me tell you the answer. The answer is yes. Transitive closure and reflexive closure, they are commutative. You can perform them in any order. The result will always be same. Can we prove it? Yes, of course. Actually, the proof is very simple, because if you notice, reflexive closure and transitive closure, they do not interfere with each other. Okay, let me explain. On one side, let me first do reflexive closure, then let me perform transitive closure. And on the other side, you can see for the relation R, first I will find the transitive closure, then I will find reflexive closure. Okay, now let me see if the final result will be same or not. Okay, so you can see we have relation R. Initially, what we have? Initially, we have relation R. Okay, so what is given to us? Relation R is given to us. Now let's assume that in the relation R, we have this type of situation that we have this vertex A and there is vertex B. Okay, and let's assume there is a path of length at least 1 from A to B. Okay, let's assume this is path of length at least 1. Okay, from A to B. Let's assume this type of situation we have in the relation R. Okay, so here also let me draw the same thing, because initially what we have? Initially we have R. Okay, so given relation R, and let's assume in the relation R we have this situation that we have two vertices AB, we have two elements in the base set AB, and there is a path of length at least 1 from A to B. Okay, so what we have here? This is a path of length at least 1. Okay, now you can see on the left side what we are finding? We are finding for relation R, first you find the reflexive closure. Okay, so what you will do first? First you will do the reflexive closure. First we will find the reflexive closure. So tell me, if I first find the reflexive closure, how to find the reflexive closure? If the graph representation of relation R is given to us, then how to find the reflexive closure of R? Very simple. We will add all the self loops. Okay, that's it. Very easy. Okay, so what we will do? A is there, B is there. Okay, A comma B are there. Everything else is same. Everything else will be as it is. Okay, but what we will do? We will add self loop. Okay, yes or no? So on all the vertices, I can say we will add self loop. So this is how you can find reflexive closure. Basically, to find the reflexive closure, what you will do? You will add all self loops. Okay. Now, after reflexive closure, on top of that, we want to find the transitive closure. Okay. For the relation R, first you find the reflexive closure. Then on top of that, you find the transitive closure. Okay, so let's find the transitive closure here. The second, that is transitive closure. If I find the transitive closure, then tell me what I will do. How to find the transitive closure if the graph representation of a relation is given to you? Very simple. What you will do to find the transitive closure? We will add reachable pairs. Yes or no? In the graph representation, we will add all the reachable edges. I can say means from a vertex I to j. If there is a path from I to k. Okay, if there is a path from I to k means from I this k is reachable. Then what we will do? Then we will put this edge. Okay, yes or no? This transitive edge we will put. Very simple. So you know that how to find the transitive closure. For that we will add all reachable pairs. We will add all reachable pairs. Okay, very simple. So let's add all the reachable pairs. Then what are we going to get? There is vertex A, there is vertex B. Already we have already found the reflexive closure, right? Okay, so you can see this reflexive closure we have already found. This reflexive closure we have already found. Now, on top of that, we are finding the transitive closure. So to find the transitive closure, we will add all the reachable pairs means this edge we will put. Okay, from A to B, we will put a edge. Okay, we will add this edge from A to B. Very simple. So this is the final result. Okay, for the relation R, first you are finding the reflexive closure, then on top of that, you are finding the transitive closure. So this will be the final result. Now let's see. If we first find the transitive closure, then we find the reflexive closure, then what will be the final result? Okay, so you can see this is the given relation R. Now, first what you do? First you find the transitive closure. Okay, so let's first find the transitive closure. Now, how to find the transitive closure that you already know, very easy. To find the transitive closure from the graph representation, what we will do? We will add all reachable pairs. Yes or no? We will add all reachable pairs. So you can see if there is a path of length at least one from A to B, means from A, this B is reachable. Okay, from A, this vertex B is reachable, means from A to B, there is a path of length at least one. So in the transitive closure, what we will do? We will add this edge from A to B. Okay, yes or no? So you can see that this A will be there, this B will be there, everything else will be as it is. Everything else will be as it is. Now we are going to add this edge, we are going to add. Okay, very good. So now what we have? We have transitive closure. Now on top of that, we want to find the reflexive closure. So then second, now we want to find the reflexive closure. How to find the reflexive closure? To find the reflexive closure from the graph representation, all you have to do, just add all self loops. Okay, so let's add all the self loops. Then what we are going to get? Then we will get, you can see everything else will be as it is. Everything else will be as it is. Okay, now we will add the self loops. Okay, that's it. So did you notice that on the LHS also, on the RHS also, the result is same? Okay, the final result is same. So you can see for the relation R, first you find the reflexive closure, then you find transitive closure, or first you find the transitive closure, then you find the reflexive closure, the result will be same. Okay, and why it is happening? Can anyone tell me what is the reason it is happening? Because reflexive closure and transitive closure, they do not interfere with each other. Did you notice one thing, that because of self loop, the reachability does not change? Just tell me a simple point. Just tell me a simple point why it is happening. Because notice, because of self loop, the reachability is not changing. Okay, tell me one thing. In a graph from A, if B is reachable, okay, let's assume from A, B is reachable by a path of length at least one. Okay, this is path of length at least one. Okay, now you tell me, if I add self loop, will the reachability change? The reachability will not change. Okay, do you agree with me? adding the self loop doesn't change the reachability. Okay, so you can see that from here, one thing you can notice, that adding self loop doesn't affect reachability between different vertices. Okay, is this clear? If I add the self loop, then remember the reachability will not be affected between different vertices. Okay, so you can see, if I add the self loop, adding self loop doesn't affect reachability between different vertices. So that is the reason you can see reflexive closure, transitive closure, they are commutative. You can perform them in any order. The final result will be same, because reflexive closure, transitive closure, they do not interfere with each other. Or I can say that adding self loop doesn't affect the reachability between different vertices. I hope you understood. Okay, very simple. So you can read this, that transitive closure, how to find the transitive closure when graph representation is given. So to find the transitive closure, we will add all the reachable pairs. To find the reflexive closure, we will add self loops. Now remember, these two operations means transitive closure, reflexive closure, they do not interfere with each other. What it means? It means that self loops do not create new reachability between different elements. Okay, because of adding self loop, new reachability between different vertices will not be created. Okay, very simple. So order doesn't matter. I hope you understood. Okay, so you can see here the proof I have given to you, that whether you do like this, means first you are finding the reflexive closure, then you are finding transitive closure, or whether you do like this, means first you are finding transitive closure, then reflexive closure, the final result will be same. So reflexive closure, transitive closure, they are commutative. Okay, you can perform them in any order, the final result will be. Closure, can I say that the result will always be same for every relation R? Can I say that? Think about it. Let me tell you the answer. Transitive closure and symmetric closure, they are not commutative. Means there are some relations, or I can say for a relation R, it may happen, it may be possible that if you first find symmetric closure, then you find transitive closure, then the result will be different from if you find transitive closure first, then you find symmetric closure. Means these two may or may not be different for a relation R. Means for a relation R, remember, they may be same or they may be different. So there is no guarantee that they will be same. So I can say symmetric closure, transitive closure, they are not commutative. Okay, I hope it is clear. Let me give you one example. Consider this relation R over the set 1, 2, 3. So this is the base set over which we are defining this relation R. In the relation R, we have two elements. In a relation, every element is a ordered pair. You already know. So you can see this is an element, two related to one, and this is another element, two related to three. Okay. Now let's see. For the relation R, first I find the symmetric closure, then I find the transitive closure. Then what will be the result? Also, for relation R, first I find transitive closure, then I find symmetric closure, then what will be the result? Okay. So let's see. First, I will find the symmetric closure of relation R. Then tell me what will be the result. For the relation R, first I will find the symmetric closure. Symmetric closure. Okay. For this relation R, if I find the symmetric closure, then what I will do? You already know that for any relation R, to find the symmetric closure, what you will do? You will take the union of R, comma R inverse. Okay, yes or no? What is R inverse? In R inverse, every ordered pair of R will be swapped. I can say that to find the R inverse, what you will do, in every ordered pair of R, these two elements you will swap them. Okay, yes or no? So then you will get R inverse, and R union R inverse, that is the symmetric closure of R. Okay, so very simple, that after finding the symmetric closure of R, what I will get, I will get 2 1, also 1 2, I will get 2 3, also 3 2. Okay, so now what we got? We got symmetric closure. So for the relation R, first we found symmetric closure. Now on top of that, we need to find the transitive closure. Means for this relation, we need to find the transitive closure. Okay, so let's see what will be the transitive closure. Transitive closure. Okay, so what is going to be the transitive closure? Let's see. Okay, you can think about the graph representation, because I told you that from set representation, if you are finding the transitive closure, it may be hectic. So you can think about the graph representation of this relation. So you can see from 2 to 1 there is age, from 1 to 2 there is age. Okay, it's like this. See, for this relation, you can make the graph representation. Okay, what I can do, it's like from 2 to 1 there is age, from 1 to 2 there is age, from 2 to 3 there is age, from 3 to 2 there is age. Okay, correct. So you can see what we found the graph representation. This is the graph representation. Okay, so this is the graph. Now now you can see what will be the transitive closure. So very easily you can see that there will be self loop on 2. Okay, so the transitive closure, you can see, also remember, from 1 to 3 there is path. Okay, from vertex 1 to 3 there is path of length at least 1, from 3 to 1 there is path of length at least 1. Okay, so the transitive closure, if you notice, okay, let me make the graph representation of transitive closure. Okay, the transitive closure graph representation, if I make, that will be like this. The transitive closure graph representation will be like this. It will be 1 2 3. Okay, like this. What we got? Basically we got the A cross A. Okay, yes or no? We got the largest relation possible on this base set. Okay, if you call it A, then basically we got A cross A. Okay, I hope you understood. Now let's see the second one. Means for the relation R, first you find the transitive closure, then you find the symmetric closure. Okay, so this is the relation R. Let me make the graph representation of relation R. So you can see 2 is related to 1, 2 is related to 3. This is the graph representation of relation R. Okay, this is the relation R. So for this relation R, first you find the transitive closure. Okay, let me find. So let me find the transitive closure. So to find the transitive closure, what I will do? From the graph representation, very easily you can find the transitive closure. Okay, so what that will be? You will just check the reachability. Okay, you can see from vertex 2 to 1, there is a path of length at least 1. From 2 to 3, there is path of length at least 1. So did you notice that? That's it. This is the transitive closure. Okay, nothing else. Actually, this is already transitive. This relation R is already transitive. So the transitive closure will be R itself. If a relation R is already transitive, then the transitive closure of R will be R itself. Okay, so you can see R itself you got. Now on top of that, what you will do? You will find the symmetric closure. You will find the symmetric closure. Okay, so let's find the symmetric closure then. The symmetric closure will be like this. Okay, 2 to 1, 1 to 2, 2 to 1, 1 to 2, 2 to 3, 3 to 2. Okay, did you see any difference between this result and this result? Yes, they are different. Yes or no? This result, they are different. Okay, is this clear to everyone? I am explaining with help of one example that transitive closure, symmetric closure, they are not commutative. Okay, so for a given relation R, this result of 1 and result of 2, that may or may not be same. Okay, means first you find symmetric closure, then you find the transitive closure, then the result may be different from first you find transitive closure, then you find symmetric closure. I hope you understood. Okay, so this is the final conclusion. So let's see a note. For a relation R, the following may or may not be same. Means for the relation R, first you find symmetric closure, then you find transitive closure, or first you find transitive closure, then you find symmetric closure. Then remember that these two may or may not be same. It means that symmetric closure, transitive closure, they are not commutative. Okay, very simple. Now this is the final conclusion. So you can see that reflexive closure, symmetric closure are commutative. Very easy. Reflexive closure, transitive closure are also commutative. But remember, symmetric closure, transitive closure, they are not commutative. So this is the final conclusion. Okay, is this clear? Very simple. So remember, reflexive closure, this is commutative with both symmetric closure, comma transitive closure. But transitive closure, comma symmetric closure, they are not commutative. I hope you understood. This is the concept commutativity of various closures. I hope you understood. Very easy. The concept was very easy. And we have seen the explanation, we have seen the counterexample, we have seen the proof. Okay, very good. Now let's study equivalence closure of a relation. So far we have studied reflexive closure, symmetric closure, transitive closure. Now, what is equivalence closure of a relation? The concept is very simple. You have a relation R, then what will be equivalence closure of that relation R? Equivalence closure of relation R will be smallest equivalence relation containing R. Okay, smallest equivalence relation that contains R. That is the equivalence closure of relation R. So let's see the definition. Equivalence closure of a relation. The equivalence closure of relation R, that is smallest equivalence relation that contains R. Very easy. Now, how to find equivalence closure of relation R? For a given relation R, to find the equivalence closure, remember equivalence relation means what? Do you know? Equivalence relation means reflexive, symmetric, transitive. Okay, do you remember? So we already know that equivalence relation, this concept, we already know that equivalence relation is a relation which is reflexive and symmetric and transitive. Okay, so how to find equivalence closure of relation R? So for the given relation R, to find the equivalence closure, you need to find, first you find reflexive closure, then you find symmetric closure, then you find transitive closure, in that order. Okay, so remember, to find the equivalence closure of R, you find reflexive, symmetric, transitive closure of R. Is this clear? For the given relation R, you find reflexive, symmetric, transitive closure of R in that order. Means for the relation R, first you find reflexive closure, then you find symmetric closure, then on top of that you find the transitive closure. From the graph representation point of view, if graph representation of relation R is given to you, then first you find reflexive closure, means you add all the self loop. Then on top of that, you find the symmetric closure. Symmetric closure, what it means? It means that if there is a unidirectional edge, then you make it bidirectional. Yes or no? Make all the edges bidirectional. Then on top of that, you find the transitive closure. How to find the transitive closure? You add all the reachable pairs. Okay. So you can see To find the equivalence closure of relation R, we will find reflexive symmetric transitive closure of R in that order. I hope you understood. Now you might be thinking, can we change this order? For example, can we do can we first find the reflexive closure, then we can find the transitive closure, then we can find the symmetric closure? Can we change this order? This reflexive symmetric transitive, this order, this can we change? If I change, will I get equivalence closure of relation R? You might be thinking, yes or no. How many of you are thinking? I told you that equivalence relation, the definition of equivalence relation you already know. Equivalence relation is a relation which is reflexive and symmetric and transitive. Now, for a given relation R, how to find equivalence closure? I told you, very easy. You will find reflexive symmetric transitive closure of relation R in that order. Means first you will find reflexive closure, then on top of that you will find symmetric closure, then on top of that you will find transitive closure. But you might be thinking that, can we change the order? What do you think? If I change the order, then will I get equivalence closure of relation R? The answer is may or may not. Okay, let me explain. Let me ask you this simple question. To find equivalence closure of relation R, can we find reflexive transitive symmetric closure? Means, can we change the order of transitive comma symmetric? This is the simple question I am asking, that to find the equivalence closure of relation R, can we do like this, that first you find reflexive closure, then you find transitive, then you find symmetric? Will this order work to find the equivalence closure of relation R? Let me tell you, this order will not work. Let me give you one example. Consider this relation over this base set 1 to 3. So this relation 2 1 2 3. Okay. Now let's do one thing. First we will find the reflexive closure, then we will find the transitive closure, then we will find the symmetric closure. Okay. So already this relation R you have. Let me make the graph representation. So the graph representation of relation R is like this: 2 related to 1, 2 related to 3. This is the relation R. Now let's first find the reflexive closure. So when I find the reflexive closure, then tell me what will happen. How to find reflexive closure when graph representation is given? Very simple, you will add all the self loops. Okay, that's very easy. You will add all the self loops. Okay, so this is the reflexive closure. Now you find transitive closure. Okay, no problem. Let me find transitive closure. So to find the transitive closure, what you will do? From the graph representation, very easily you can find the transitive closure. All you have to do, just add all the reachable pairs. All the reachable pairs we are going to add. Okay. So you can see there is 2, 1, 3. Okay. This graph will be as it is. This graph will be as it is. Okay. Now, is there any reachable pair which is missing? No. You can see that no other reachable pair is missing. Yes or no? Okay. So that's it. This is the transitive closure. Okay. So we got transitive closure. Now let's find the symmetric closure. Okay. After transitive closure, you find the symmetric closure. So let's find the symmetric closure now. So how to find the symmetric closure when graph representation is given? You will make every edge bidirectional. Yes or no? Okay. In the graph representation, to find the symmetric closure, you will make every edge bidirectional. Okay. So it will happen like this, that 2 1 3. Okay, make every edge bidirectional. Tell me one thing, this result that you got, is it equivalence relation? A simple question I'm asking. Is it equivalence relation? Remember what we did? For the given relation R, first we found reflexive closure, then we found transitive closure, then we found symmetric closure in this order. Now, the result that we got, can I say it is a equivalence relation? This result, is it a equivalence relation? No, it is not equivalence relation. It is reflexive, it is symmetric also, but it is not transitive. You can see one is related to two, two related to three, but one is not related to three. Yes or no? This is not transitive. So overall, I can say, did you notice that this is not equivalence relation? This is not equivalence relation. Why? What is the reason? Because this is not transitive. Is this clear? Okay. Now you might be thinking, we already found transitive closure. Then how is it possible that this final result is not transitive? So let me tell you, when you found transitive closure, now this result is transitive. But after that, you found symmetric closure. After finding transitive closure, you found symmetric closure, and symmetric closure can disturb the transitivity. They interfere with each other. Because of symmetric closure, transitivity can get disturbed. Okay, you can notice for this relation you found transitive closure, then you got transitive relation. Okay, so remember this is transitive relation. But remember, on top of that, you are finding symmetric closure. So symmetric closure can disturb the transitivity. So this final result that you got, this is not transitive. So this is not equivalence relation. If this result is not equivalence relation, then it is not a equivalence closure also. Because what is equivalence closure of relation R? Equivalence closure of relation R, that is smallest equivalence relation containing R. Okay, yes or no? So I hope you understood that we cannot just randomly do these operations in any order. Okay, first first you should do reflexive closure, then symmetric, then transitive. If you want to find equivalence closure of relation R, then first you need to find reflexive closure, then you find symmetric closure, then you find transitive closure. In this order you must do. Then you will get equivalence closure of relation R. Okay, but don't interchange symmetric comma transitive. If you do that, then the result may not be equivalence closure of relation R. Okay, with help of example I have proven it. Very simple. I hope you understood. Just for sake of practice, let's see, if this relation R is given to you over this base set 1 to 3, then what will be equivalence closure of this relation R? To find the equivalence closure of relation R, you will find reflexive closure, then symmetric closure, then transitive closure, in that order. Okay, in that order that you already know. So let's see. So let's see what you will do. First, you will find reflexive closure. What is the relation R? Relation R is like this. Let me make the graph representation of relation R. So relation R is like this: 2 related to 1, 2 related to 3. Okay. Now let's find the reflexive closure first. So how to find the reflexive closure when graph representation is given? Then you will add all the self loops. Yes or no? Okay, the graph will be as it is. You will add all the self loops. This is the reflexive closure. Now you find symmetric closure. Okay, so let's find symmetric closure. How to find symmetric closure? You will make every edge bidirectional. Okay, yes or no? This graph will be as it is. Every edge you will make bidirectional. Okay, very easy. Now, now on top of that, you will find the transitive closure. Okay, how to find the transitive closure? That is very simple. 2 1 3. Okay, so transitive closure means you will add all the reachable pairs, yes or no? From the graph representation, finding transitive closure is very easy. You will add all the reachable pairs. So we already have this graph. Now you can see that from 1 to 3 there is path of length at least 1. From 3 to 1 there is path of length at least 1. Okay, so this also you will put. What we got basically A cross A. Okay, if this is A, then we got basically A cross A. And yes, this is equivalence relation. This is the equivalence closure. Okay, this is the equivalence closure. This is the equivalence closure of relation R. I hope you understood. Is this clear? Now let's see a method 2 for finding equivalence closure. And this is easier method. Very quickly you can find the equivalence closure. You don't even have to find the symmetric, reflexive and transitive closure. Means, remember I told you, to find the equivalence closure of relation R, first you find reflexive closure, then symmetric closure, then transitive closure. But you can directly find equivalence closure very easily. Okay, how to do that? Remember the definition of equivalence closure. Equivalence closure means equivalence closure of relation R. What is that? That is smallest equivalence relation containing R. Okay, so you just focus on the relation R. In the relation R, you notice one thing. Let's make groups. Okay, let me make groups, because if you remember, equivalence relation will divide your base set into groups. Do you agree with me? Okay, this we have already seen in our equivalence relation chapter. Okay, you already know that equivalence relation on set A, equivalence relation on set A, equivalence relation on set A partitions partitions A into equivalence classes, or I can say groups. Yes or no? Partitions A into groups, and these groups are called equivalence classes. These are called equivalence classes. Okay, do you agree with me? So that same concept you can use. So let's just make the groups from this relation R. Okay, you can see in this relation R already you can see that 2 is related to 1. So it means that 2 comma 1 will be in the same group. Do you agree with me? See, very simple method I am telling you, that any relation R is given to you on any base set A, then how to find equivalence closure of relation R? There is a very quick method. I can say very quickest method. That is like this. That is based on this concept. We already know that equivalence relation on a base set A will partition the base set into groups, or I can say these groups are called equivalence classes. So you can see here this relation R you have. So let's see the groups. In the relation R, you can already see that 2 is related to 1. It means that 2 comma 1 will be in the same group. No doubt. Also, you notice 2 is related to 3. 2 is related to 3. So 2 comma 3 will be in the same group. Now, did you notice that 2 comma 1 comma 3 they are in the same group? They are in the same group. Same group, or I can say that same equivalence class. They are in the same equivalence class. Okay. So finally, now I can say the equivalence closure will be what? This itself is your equivalence class for the equivalence closure. Okay, so let me just write it here, that this is the equivalence closure of R. This is the equivalence closure of R. Okay, so what is your equivalence closure of R? That is basically 2, 1, 3. These are in the same group. Okay, if they are in the same group, then you can simply say that they are related to each other. Okay, 2 related to 1, 2 related to 3, 1 related to 3. Okay, yes or no? They are related to each other, and of course there is self loop also. Okay, they are related to each other. That's it. This is your final answer. Equivalence closure of R. This is the equivalence closure of R. Did you understand? Tell me. Let me know. For example, just for sake of practice, let's assume that we have this relation R, that is 1 related to 2, 3 related to 4, and 4 related to 5. Okay. And let's assume on the set, on the set 1, 2, 3, 4, 5. Now you tell me what will be equivalence closure of R. We need to find equivalence closure of R. So what that will be? Equivalence closure of R, very easily you can find. All you have to do, just see that will be formed. Okay, equivalence closure of R. You just see the groups. You just see the groups. The groups are like this. You can see one is related to two, so they are in the same group. Okay, nice. Also, you can see that 3 comma 4 are 3 is related to 4, so 3 comma 4 in the same group. 4 is related to 5, so 4 comma 5 in the same group. That's it. Two groups will be there. Two groups will be there, means this is equivalence class 1, this is equivalence class 2. And now finally, what will be your equivalence closure? Okay, the equivalence closure will be like this, that okay, 1 is related to 2, 2 related to 1. Okay, self loop, means this is a group. Within a group, everyone is related to everyone. Okay, within a equivalence class, every element is related to every other element. Okay, also itself, means self loop. So remember, within a equivalence class, every element is related to every element. Every element within a equivalence class is related to every element. Okay, so you can see 3, 4, 5. That also will be like this. Okay, that's it. This is your final answer. I hope you understood. This is the final answer. Of course, there is another method. What is that? Another method is, for the relation R, you will find reflexive closure, then you will find symmetric closure, then you will find transitive closure. The result will be equivalence closure of R. But this method is very fast. I hope you understood this method. Okay. Now tell me the answer for this question. Very interesting question. And I hope in the GATE exam they ask you this question. Very interesting. Tell me, which of the following is the equivalence closure of relation R? 6 options are given to you. Basically, all the orders I have put here: reflexive, symmetric, transitive, symmetric, reflexive, transitive, reflexive, transitive, symmetric, symmetric, transitive, reflexive, transitive, symmetric, reflexive, transitive, reflexive, symmetric. My question is very simple. Which of the following will definitely give me equivalence closure of relation R? Which of the following is the equivalence closure of relation R? To find the equivalence closure of relation R, which of the following will definitely guaranteed give me the equivalence closure of relation R? We already know that this first one will give me equivalence closure of relation R. Reflexive, symmetric, transitive, in that order. Okay, reflexive, symmetric, transitive, in that order. This will give me equivalence closure of relation R, that we already know. But we also know one more thing. What is that? Reflexive comma symmetric, they are commutative. We can change their order. So reflexive comma symmetric, they are commutative. We can change their order. First, you can find symmetric closure. Then on top of that, you can find reflexive closure. Then you can find transitive closure. So this is also perfect. Means these both are same. Yes or no? These both are same. Okay, very good. Notice one thing. Transitive comma symmetric, I cannot exchange. Yes or no? transitive comma symmetric, this order I cannot change. I told you symmetric closure, transitive closure are not commutative. You cannot change their order. Do you remember? Symmetric closure, transitive closure, they are not commutative. You cannot change their order. So this is no. What about this one? Symmetric, transitive, reflexive. Notice one thing, that reflexive closure is commutative with symmetric as well as with transitive. Now just focus on this. Symmetric, reflexive, transitive. Can I interchange these two? Can I change the order of these two? Only focus on these two. Can I change the order of these two? Reflexive, transitive. Can I change the order? Transitive, reflexive. Yes, I can do that. Okay, so yes. Now remember that this is also same to this. Yes or no? Because please understand that symmetric, reflexive, transitive. Now reflexive comma transitive, they are commutative. So I can change their order. I can change. So you can see that this fourth one, that is also equivalence closure. What about the fifth one? Transitive, symmetric, reflexive. No, I cannot change the order of transitive comma symmetric. What about this one? Transitive, reflexive, symmetric. No, I cannot change the order of transitive comma symmetric. After symmetric, transitive should be there. You cannot put symmetric after transitive. Okay, so finally the answer will be option A, B, D, or I can say 1, 2, 4. A student has given correct answer in the chat. Very good, excellent. I hope you understood the concept. Okay, so finally this is the result. You can see that transitive closure must come after symmetric closure. Yes or no? To find the equivalence closure, transitive closure must come after symmetric closure. That's it. Okay, because reflexive closure is commutative with symmetric as well as transitive closure, but symmetric closure, transitive closure, they are not commutative. After symmetric, transitive should be there, or I can say transitive closure must come after symmetric closure. So you can see this will work: reflexive, symmetric, transitive, in that order. It will provide you equivalence closure of relation R. This is also perfectly fine. After symmetric, transitive should be there. After symmetric, transitive should be there. After symmetric, transitive should be there. Okay, that's it. Very simple, very good. Let's solve GATE CS 2004 question. Consider the binary relation. This relation S is given to us. The base set is 0, 1, 2. On this base set 0, 1, 2, this binary relation is defined. The reflexive transitive closure of S is the reflexive transitive closure of. Here it will be off. Okay, it is not is. It will be off. It will be off. Okay. So the question is asking reflexive transitive closure of S. Remember, reflexive transitive closure means first you find reflexive closure, then you find transitive closure. Okay. But one interesting thing, we have already seen that reflexive closure, transitive closure, they are commutative. So first you can find transitive closure, then you can find reflexive closure, or first you can find reflexive closure, then you can find transitive closure. The result will be same, because reflexive comma transitive closure, reflexive closure, transitive closure, they are commutative. You can perform them in any order, the result will be same. Okay, so let's solve this question. Here the base set is just 0, 1, 2. Okay, this is the base set. Let me call it A. 0, 1, 2, only three elements in the base set. And this relation we are defining, x is related to y when y is equal to x plus 1. So I can make the graph representation of S. Remember, to find the closure, to find transitive closure, to find reflexive closure, to find symmetric closure, the best method is graph representation. Particularly for transitive closure, to find transitive closure of a relation, The best method is graph representation. So first let me make the graph representation of relation S. So in the relation S we have 0, 1, 2. These are the elements in the base set. Now you can see x related to y when y is equal to x plus 1. So you can see that 0 will be related to 1. You can see 1 will be related to 2. That's it. This is the graph representation of S. Now the question is asking, we need to find reflexive transitive closure. So first you can find reflexive closure, then you can find transitive closure, or first you can find transitive closure, then you can find reflexive closure. Both are fine. Okay, so remember from here, first you can find reflexive closure. Let me find the reflexive closure first. The reflexive closure, that will be what? To find the reflexive closure from the graph representation, all you have to do, just add all the self loops. Okay, so let me add all the self loops. So self loop here, self loop here, self loop here. That's it. This is the reflexive closure. Okay, now you find the transitive closure. On top of that, you find the transitive closure. Okay, how to find the transitive closure when graph representation is given? To find the transitive closure, you will add all the reachable pairs. Yes or no? How to find transitive closure, that you already know, that add all reachable pairs. That's it. That's it. Add all reachable pairs. Okay, so let me add all the reachable pairs. So you can see 0. This graph is as it is, 0, 1, 2. Okay, this graph is as it is. This graph, you can see, this is as it is. Now you can notice how to find the transitive closure of this graph. This is the graph. How to find transitive closure? You will add all the reachable pairs. You can notice from 0 2 is reachable, or I can say that from 0 to 2 there is a path of length at least 1. From this vertex 0 to vertex 2 there is a path of length at least 1. Okay, so this age I will put. Yes or no? Add all the reachable pairs. From 0 to 2 there is a path of length at least 1. So this age I will put. Now is there any other age that I need to put to find the transitive closure? Is there any reachable pair? No, there is no more reachable pair. Okay, yes, we have covered everything. Yes or no? You can notice that from 2 to 1 there is no path. From 2 to 0 there is no path. Okay, yes or no? From 1 to 0 there is no path. So that's it. This is your final answer. Okay, so remember, this is the final answer. Now in the graph, in the set representation, what it will become? We have final answer here. So in the set representation, what it will become? It will become like this, that x, y, such that x is related to y, such that y is equal to or I can say, sorry, y is greater than equal to x. Okay, yes or no? So this will become the final answer. I hope you understood. Actually, let me take a bigger base set. See, just let me take a bigger base set. Let's assume that your base set is like this: 1 2 1 2 3 and so on. Let's assume this is the base set. Base set is natural numbers, let's assume. Okay, or I can say positive integers. Positive integers. Okay, now what is our relation as? Our relation as is x is related to y when y is equal to x plus 1. Okay, yes or no? This is the relation where x comma y, they come from a. Okay, so now let's find the reflexive transitive closure of S. First you can see what will be the graph representation here. The graph representation will be like this, that 1 will be related to 2, 2 will be related to 3, 3 will be related to 4, and so on. This is the graph representation. Now what will be reflexive transitive closure of this relation S? What that will be? Now you can easily see reflexive closure. To find the reflexive closure, you will just add the self loop. That's it, nothing else. Okay, you will add the self loop. To find the transitive closure, what we will do? We will add reachable pairs. Now you can see from 1 to 3 there is a path of length at least 1. From 1 to 4 there is a path of length at least 1. From 2 to 4 there is a path of length at least 1. From 2 to 5 there is a path of length at least 1. Yes or no? Means to find the transitive closure, what I need to do? I need to add this edge, I need to add this edge, I need to add this edge, I need to add this edge. Because from 1 to every other vertex there is a path of length at least 1. Means from 1 every other vertex is reachable by a path of length at least 1. Yes or no? Similarly, from 2 every bigger number is reachable by a path of length at least 1. From 2 to 4 there will be edge, from 2 to 5 there will be edge, because from 2 to 4 there is a path of length at least 1. From 2 to 5 there is path of length at least 1. From 3 to 5 there will be edge, from 3 to 6 there will be edge, and so on. So did you notice that the reflexive transitive closure of S, that will be like this: 1 related to 2, 2 related to 3, 3 related to 4, 5, and so on. Now, reflexive closure means self loop. You add self loop. Okay. And transitive closure, what it means? It means that you add all the reachable pairs. All the reachable pairs by a path of length at least 1. All the pairs reachable by a path of length at least 1. You add all of them. Okay. Similarly, from 2 to 4, from 2 to 5, from 2 to 6, and so on. Okay. Similarly, from 3 to 5. Okay. From 3 to 6, and so on. I hope you understood my point. So finally, what will be reflexive transitive closure of S? What that will be? That will be X, Y, such that you can see that Y is greater than or equal to X. Okay. I hope you understood. When you take positive integers as the base set, then it is more, I can say, more understandable what is happening. But of course, in the given question, the base set is only 0, 1, 2. So this will be your reflexive transitive closure. And here you can easily see that X is related to Y if and only if Y is greater than equal to X. You can see 0 related to 1, 0 related to 2, 1 related to 2, 2 related to only 2. You can see also self loop is there. So you can see that 0 is related to 0, 1, 2. 1 is related to 1, comma 2. 2 is related to only 2. So the answer will be that reflexive transitive closure, that will be Y greater than equal to X. Okay, so the answer will be option B. This will be the answer. I hope you understood. Remember, in the same question, first you can find transitive closure, then you can find reflexive closure, then also you will get the same answer, because reflexive closure and transitive closure, they are commutative. Okay, so let me just write it here just for sake of understanding. Remember, you can find transitive first. That's perfectly fine. First you can find transitive closure, and then you can find reflexive closure, because they are commutative. First you can find transitive closure. Okay, so when I find the transitive closure, then what I will get? I will add all the reachable pairs. So this is what I will get. Okay, now you can find the reflexive closure. Okay, so now when I find the reflexive closure, this is what I already have. Now reflexive closure means you add all the self loops. Okay, so you can see that this is the answer that you will get whatever you do, because reflexive closure and transitive closure, they are commutative. You can perform them in any order. But remember, symmetric closure, transitive closure, they are not commutative. So if the question asks you symmetric transitive closure, then you have to perform first symmetric then transitive. Don't do transitive then symmetric. Okay, because symmetric closure, transitive closure, they are not commutative. Okay, I hope you understood. Now let's see a small note about m power 0. What is M? M is the matrix representation of a relation R. So M is the adjacency matrix of a relation R. Then what is power 0? In the previous lecture, we have discussed power of adjacency matrix like M power 1, M power 2, M power 3, M power 4, M power K. Now, what is M power 0? Let's discuss it. This is a very small point. This is a small question I want to ask. For any relation R, let M be the matrix representation of R. Then what is M power 0? Whatever relation R you take, let's assume that M is the matrix representation of R. Then what will be M power 0? What do you think? What will be M power 0? Let me tell you the answer. Notice one thing, that what is M power 1? M power 1, that is same as M. Or I can say that M power 1, of course, that is same as M. Can I write it M power 1 plus 0? Can I write it M power 1, M power 0? So just tell me a small point. M power 1, M power 0, that is same as M power 1. So what should be this M power 0? Tell me. Or it's like this. Whatever M power R you take, I can write it M power R plus 0. I can write it M power R, M power 0. So M power R, M power 0, that is same as M power R. So what should be this M power 0? Remember, with a matrix, which matrix should I multiply so that I get this same matrix as it is? Are you getting my point? Let me know. Which matrix should I multiply so that I get this same matrix as it is? The answer is identity matrix. Yes or no? Okay. Identity matrix, yes or no? In the linear algebra, you study this identity matrix. When you multiply, then what you will get? Then you will get the matrix will as it is you will get. Basically, identity matrix does not affect the multiplication. Okay, so I can say that it is identity matrix. Is this clear? Let me know. So very easy that it will be identity matrix. I hope you understood, because you already know this, that any matrix multiplied by identity matrix, that will be same as M. Okay. So very easily you can see that for any relation R on a set of n elements, let M be the matrix representation, then M power 0 is always the identity matrix. Okay. So let's assume that your base set is A. Okay. And let's assume in the base set we have total n elements like 1, 2, 3, and so on. Total n elements. Then remember, M power 0. M power 0 is always identity matrix. Always. It's always identity matrix. Okay. And what is identity matrix? In the identity matrix, the main diagonal elements are all ones, and all the remaining elements are zero. All the remaining elements are zero. Okay. I hope you understood. So very easy that for any relation R on any set of n elements, M power 0, where M is the matrix representation of R, M power 0 is always the identity matrix. Okay. For example, if your base set is, let's assume, 1, 2, 3 or ABC, if your base set is ABC, then what will be M power 0? M power 0 will be a 3 by 3 identity matrix. Okay. Because in your base set you have total 3 elements. So it will be a 3 by 3 identity matrix. Okay. That's it. I hope you understood that M power 0 is always the identity matrix. Actually, M power 0 is always the identity matrix. One way to understand is using this logic, that m power r that is same as m power r plus 0, or I can say m power r multiplied by m power 0. So what should I multiply with the matrix so that I get the same matrix? The answer is identity matrix. One logic is this, to understand that m power 0 is the identity matrix always. But there is another logic to understand why m power 0 is identity matrix always. There is another logic also. So let me tell you that logic also. That is also very nice logic. Do you remember in the previous lecture we have seen powers of adjacency matrix of a relation? So let me just quickly do the recap. In the previous lecture, we have already seen what m power k represents. M is the matrix representation of relation R, or I can say M is the adjacency matrix of relation R. Then what is M power K? What does M power K represent? I told you that M power K represents existence of walk of length exactly K in the diagram of relation R. Means in the graph representation of R, existence of walk of length K that is represented by M power K. What it means? It means that in m power k, cell a comma b will be 1 if and only if there is a walk of length k from a to b. Okay, so remember m power k represents existence of walk of length exactly k. For example, m power 2 represents existence of walk of length 2, m power 3 represents existence of walk of length 3, m power 1 represents existence of walk of length 1. So similarly, what m power 0 will represent? Similarly, m power 0 will represent existence of walk of length 0. Is this clear? M power 0 will represent existence of walk of length 0 in the graph representation of R. Okay. Now you tell me, walk of length 0. When can you have walk of length 0? Walk of length 0. Length 0 means there is no edge. The length of a walk, that is number of edges in this walk. Walk of length 0. What is the meaning of walk of length 0? Tell me. Walk of length 0 means there should be no edge. This is a walk of length 0. This is a walk of length 0. This is a walk of length 0. Yes or no? These are the walks of length 0. And remember, m power 0 represents I can say, yes, m power 0 represents existence of walk of length 0. Okay, so you can easily see that m power 0 what it will be. M power 0 what it will be. If I write here, for example, ABC, here if I write ABC, then what will be m power 0? M power 0 represents existence of walk of length 0. Tell me, from A to B, can you have walk of length 0 from A to B? Whatever graph representation, whatever graph you take, you have A, you have B, you have C. Whatever graph you take. Okay, tell me one thing. Can you have walk of length 0 between different vertices? Between different vertices, can you have walk of length 0? Walk of length 0 means there should be no edge. Length of a walk means the number of edges in that walk. Walk of length 0 means there should be no edge. So between different vertices, can you have walk of length 0? No. Walk of length 0 simply means that you are here, and walk of length 0 means you will go only here from A to A. But there should be no edge. Like, don't consider the self loop. If I take only this vertex A, in the previous lecture, we have already seen this. In the previous lecture, I have already discussed about walk of length 0, walk of length 1. Self loop is walk of length 1. But only single vertex, that is walk of length 0. So you tell me, m power 0 represents existence of walk of length 0. So from A to B, does there exist walk of length 0? No. From A to C, is there existence of walk of length 0? No. From B to A, is there existence of walk of length 0? No. From B to C, is there existence of walk of length 0? No. From C to A, from C to B, is there existence of walk of length 0? No. Because between different vertices have you cannot have walk of length 0. What about A to A? Yes, a single vertex represents walk of length 0. A single vertex represents walk of length 0. A single vertex represents walk of length 0. So that's it. This is m power 0. And this is identity matrix. This is identity matrix of size 3 by 3. Did you understand? Let me know. Very easy. So this is what I'm saying, that whatever relation you take on any base set, m power 0 will always be identity matrix. And what is m here? M is the matrix representation of R. So for any relation R, if M is the adjacency matrix, or I can say if M is the matrix representation of R, then M power 0 is always the identity matrix. The logic is very simple, because M power 0 represents existence of walk of length 0. Okay. Remember this recap. Let me just, because in the previous lecture, actually, we have seen this. Whatever graph if I take, for example, let me take this graph A, B, and let's assume that there is a self loop here. Let's assume C here and D here. Okay, and D here. So let's assume this is the graph. Now in this graph, let me tell you, if I write, for example, A, if I write like this from B to B, and if I write B here, then remember here, this is walk of length 1 from B to B. This is walk of length 1 from B to B. Okay, but remember, this is walk of length 0, because length of a walk means number of edges. Here there is no edge. Here there is no edge. So this is walk of length 0. This is walk of length 0. And here this is also walk of length 0. Okay. Remember, from A to A, there is no walk of length 1. Okay, yes or no? You can notice from A to A, because there is no self loop. From A to A, there is no walk of length 1. Okay. But from B to B, there is walk of length 1. This B to B, this self loop, this is walk of length 1. Okay. I hope you understood. For example, if I write C, now this is walk of length 0. For example, if I write D, this is walk of length 0. So I can say that in any graph, whatever graph you take, every vertex, remember, whatever graph you take, every vertex has a walk of length 0. Every vertex has a walk of length 0 from itself to itself. Okay, you can see this is walk of length 0 from A to A. From A to A. From A to A. And this is walk of length 1 from B to B. Okay. For example, this is walk of length 0 from B to B. Okay. For example, this is walk of length 0 from C to C. So remember, whatever graph you take, every vertex has a walk of length 0 from itself to itself. Okay. Whatever vertex you take, there exists a walk of length 0 from itself to itself. But remember, don't put self loop, because self loop is walk of length 1. I am saying that whatever graph you take, every vertex has walk of length 0 from itself to itself. Whatever vertex you take, that has walk of length 0 from itself to itself. And m power 0 represents existence of walk of length 0. So that is the reason you can see that from A to A, there exists a walk of length 0. From B to B, there exists a walk of length 0. From C to C, there exists a walk of length 0. But between different vertices, we don't have walk of length 0. So you can see that m power 0, that is identity matrix. Very simple. Now let me tell you a note about reflexive transitive closure of a relation R. This is a small note, very easy to understand, but they can ask you some conceptual question here. So this is a note about reflexive transitive closure of a relation R. So you can see, let's assume that M is the matrix representation of relation R. Relation R is a relation on n elements, means the base set has n elements, and on this base set a relation R is defined. M is the matrix representation, or I can say M is the adjacency matrix of relation R. Okay. In the previous lecture, we have already seen what will be the matrix representation of transitive closure of R. Do you remember that? We have already seen that the matrix representation of transitive closure of R, what that will be? Matrix representation of relation R is given to you. Then what will be matrix representation of transitive closure of relation R? So matrix representation of transitive closure, that will be equal to what? That will be equal to m power, that will be equal to m power 1 or m power 2 or m power 3 or and so on. What is the worst case of transitivity? Tell me, till when should I go? The matrix representation of transitive closure of relation R, that will be m power 1 or m power 2 or m power 3 and so on. Till when should I go? I should go till m power n. This is the worst case of transitivity. I told you in the previous lecture, worst case of transitivity. Okay. So this is how you can find transitive closure of R. Now, if the question asks you reflexive transitive closure, see, this is only transitive closure. So you are going from m power 1 to m power n. Okay. And you are doing the OR. Now, if the question asks you reflexive transitive closure of R, reflexive means self loops, yes or no? Okay. So if the question asks you reflexive transitive closure of R, then what will be the matrix representation? Then the matrix representation will be like this. So the matrix representation of reflexive transitive closure, okay, the matrix representation of reflexive transitive closure of R, what that will be? Means MRTC. Reflexive transitive closure we are finding. So the matrix representation of reflexive transitive closure, what that will be? For reflexive, you will start with m power 0, because what is m power 0? That is identity matrix. Yes or no? This will give you all the self loops. Do you agree with me? Tell me, do you agree with me that m power 0 will give you all the self loops? M power 0 is the identity matrix. So to find the reflexive closure, we need to find reflexive transitive closure. So first you will find reflexive closure. For that you do m power 0, or then everything, then you find transitive closure. So for that you will do this m power 1, m power 1, m power 2, or m power n. Okay, there is no problem. Very good. Did you understand? Let me know. So you can easily see, we want to find reflexive transitive closure. To find reflexive closure, you will add m power 0, because m power 0 is the identity matrix. So it will give you all the self loops. To find the transitive closure, you have this formula, m power 1 to m power n. Now something interesting that I want to tell you. What is that? Something interesting is that, see, when you are finding transitive closure, then you are going from m power 1 to m power n, because this m power n was giving you this m power n. This was capturing the worst case of transitivity. But when you are finding reflexive transitive closure, then you will start from m power 0. You don't have to go till m power n. You can go till m power n minus 1. That is enough. This is what I'm saying, that for reflexive you will start with m power 0, but for, if you are finding reflexive transitive closure, then you don't have to go till m power n. You can go till m power n minus 1. This will be enough. If you want to go till m power n, that is fine. You can go. If you want to go till m power n, that is perfectly fine. You can go. But that is redundant. This will be redundant. Why this is redundant? This is redundant here. This is redundant here. Okay. What is the reason this is redundant? You might be thinking that for transitive closure, this is not redundant. When you are finding transitive closure, then m power n, this is capturing the worst case of transitivity, and it is not redundant. But when you are finding reflexive transitive closure, then this m power n, this is redundant. So what is the reason? Anyone? Anyone want to tell me what is the reason? What could be the reason that for reflexive transitive closure, this m power n is redundant here? The reason is very simple. Because whatever it will capture, it is capturing the worst case of transitivity, and that worst case of transitivity will be captured by m power 0. This is what I'm saying. Remember this m power n, it was capturing the worst case of transitivity. But that worst case of transitivity, you can capture using m power 0. Okay, that is the reason we can go from m power 0 to m power n minus 1 to find the reflexive transitive closure. Okay, if you did not understand, don't worry, let me explain. Let me explain. You can see that to find the matrix representation of transitive closure of R, matrix matrix representation of transitive closure, what we were doing, we were going from m power 1 to m power n. Okay, we were doing the OR. So here you can easily see this m power n, we were going till m power n because it was capturing worst case of transitivity. Do you agree? It was capturing worst. Do you remember in the previous lecture we have already seen this? It was capturing worst case of transitivity. Yes or no? This m power n, this was capturing worst case of transitivity. And what was worst case of transitivity? What is that? What is the worst case of transitivity? So you can see worst case of transitivity, that was like this. If you have total n elements like a1, a2, a3 and so on, total n elements if you have, then what is the worst case of transitivity? a1 related to a2, a2 related to a3 and so on, like this. Now you will be thinking that this is the worst case of transitivity. If you have n elements in the base set, total n elements, then you can see this is the worst case of transitivity. But no, 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 no. The worst case of transitivity is like this, a1 to a1. You can see this is the worst case of transitivity. Did you understand? I am saying that a1, then there is a2. Or basically, you understood the point. You understood the point that this is the worst case of transitivity. This is the worst case of transitivity. Means a1 related to a1. This is the worst case of transitivity. And this worst case of transitivity, a1 related to a1, what is the length of this walk? Can anyone tell me what is the length of this walk? What is the length of this walk from a1 to a1? Tell me. From a1 to a1, what is the length of this walk? From a1 to a1. The length of this walk. You can see the length of this walk, that is n. Okay, you can easily see the length of this walk, that is n. And tell me, existence of length of walk n, who will capture? Existence of walk of length n, existence of walk of length n is captured by whom? Existence of walk of length n is captured by whom? It is captured by m power n. So this worst case of transitivity is captured by whom? It's captured by m power n. Did you understand? Very simple. I am saying that worst case of transitivity that is captured by m power n. Okay, this m power n, this is capturing the worst case of transitivity. But what is the worst case of transitivity? The worst case of transitivity that is basically the worst case of transitivity that is basically a1, a2, and so on an, and so on like this. This is the worst case of transitivity. Yes or no? From a1 to a1. Okay, this is worst case of transitivity. I hope you understood. So I am saying that m power n, it is capturing the worst case of transitivity, and this is the worst case of transitivity from a1 to a1. This walk of length n, this is the worst case of transitivity. It is captured by m power n. But basically, what this m power n is capturing, it is basically capturing a1 to a1 means this self loop, right? Do you agree with me? It's like because of m power n, because of m power n, a self loop will be contributed which is not contributed by all the previous ones. Yes or no? All these people, they could not provide you this self loop, means they could not capture this worst case of transitivity, so they could not provide you this self loop. But this m power n is providing you this self loop, or I can say this m power n is capturing this worst case of transitivity, so this m power n will provide you this self loop. Now you tell me, if I add m power 0 when we are having reflexive transitive closure, and I add m power 0, then that m power 0 will provide me self loop, so I don't need this m power n. Do you agree with me? Let me know. Okay, so you can see that this m power n, this is capturing worst case of transitivity, and this is the worst case of transitivity. And here what will happen? Finally I can say that m power n contributes, a1 which 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 other m power I may may fail to capture. Okay, is this clear? So very simple point that the worst case of transitivity is this, and m power n will contribute a1 means this self loop. Okay, a1 which other m power I may fail to capture. Okay, that's it. That's it. So finally you can see that if my purpose is reflexive transitive closure of R, okay, my purpose is to find the matrix representation of reflexive transitive closure of RTC, reflexive transitive closure of R. Okay, then for reflexive, I will start with m power 0 because m power 0 will be the identity matrix. This will give me all the self loops. Yes or no? This will give me all the self loops. So I will start with m power 0 because I want reflexive. Okay. Now because I want transitive, so m power 1, m power 2, m power n minus 1. That is enough. I don't have to go till m power n. Okay, this is more than enough. This is more than enough. This is matrix representation of reflexive transitive closure. Okay, but remember, if I only want transitive closure, I don't want reflexive closure, then the matrix representation of transitive closure, for that I will start with m power 1 or m power 2 or m power 3 and so on. I have to go till m power n. Okay, this will capture the worst case of transitivity. But here, when you are finding reflexive transitive closure, then this m power 0 will capture all the self loops. This m power 0, this will capture all the self loops. Okay, is this clear? So it is capturing all self loops. Okay, I hope you understood. Very simple. Clear? Also, tell me a small point, just a small point. If the question says that the given relation is already reflexive, if this is already given to you, the question is asking transitive closure, but the question is mentioning that you have reflexive relation already. Your relation is already reflexive, means your relation already has all the self loops. Now, for a reflexive relation, if you are finding transitive closure, then that is same as reflexive transitive closure. Do you agree with me? Yes or no? For a reflexive relation, if you are finding transitive closure, that is same as finding reflexive transitive closure. Okay, so for that, what you will do? You can you can start with m power 1, because you are finding transitive closure. Your relation is already reflexive. So m power 1 will capture all the reflexive pairs. Your relation is already reflexive. So all the self loops are captured by m. Okay, so you can start with m power 2, and you have to go only till m power n minus 1. Because remember, your relation is already reflexive. So all self loops are captured here. All self loops captured here. All self loops captured by m for reflexive relation. For reflexive relation, your relation is reflexive. So already your relation is reflexive. So this m power 1 will capture all the self loops. All self loops are captured by m for reflexive relations. Okay, so you can easily see that you have to go only from m power 1 to m power n minus 1. Okay, because ultimately you are finding reflexive transitive closure. Your relation is already reflexive, and you are finding transitive closure. So that is same as basically, that is same as finding reflexive transitive closure. But now you don't have to start from m power 0, because already your relation is reflexive. So m power 1 will capture all the self loops. Okay, so you can just do this. That's it. Okay, these small understanding, are they clear? Please tell me. See, all these variations you cannot solve. You cannot by heart all these things. If you try to remember all these things, okay, let me remember, let me by heart, let me not understand, let me do the rote learning. Okay, I will remember all the theorems, all the points, all the important points, everything. Then that will not work. Just understand the logic and it will become very smooth. It will become very enjoyable if you just understand the logic. So I hope you understood everything we have seen very clearly. Okay, with proof. I hope you understood. Now at the end, let's see a optional topic, that is proof of power of adjacency matrix of a relation theorem. In the previous lecture, also in this lecture, we have seen power of adjacency matrix of a relation. For a relation, we have adjacency matrix. Then what is the significance? What is the meaning of power of that adjacency matrix? Like m power k. What is the significance? What is the meaning of m power k for a relation R? So that theorem we have already seen in the previous lecture. Also in this lecture also we have done the recap. Now what is the proof of that? So that proof we will see. Okay, this is optional for the gate exam. You can skip it. Okay, so let's just see quickly the proof. First, let me tell you the theorem. What was the theorem? So you can see power of adjacency matrix of a relation. So you have relation R, and for this relation R, M is the matrix representation, or I can say M is the adjacency matrix for relation R. Then what does M power K represent? So we have already seen this theorem. You can see this important theorem that M power K represents existence of walk of length k in the diagram of R. Okay, remember, m power k represents existence of walk of length k. For example, m power 3 represents existence of walk of length 3. M power 4 represents existence of walk of length 4. What it means? It means that in m power k, cell AB will be 1, entry AB will be 1 if and only if there is a walk of length k from A to B. Okay, so basically m power k represents existence of walk of length k. Easy. Now, what is the proof of this theorem? This is the question, that how can I prove it? How can I prove that if there is a walk of length k from A to B, then in m power k, the entry AB will be 1. Also, another side, because there is if and only if. What is another side? Another side is that in m power k, if entry AB is 1, then can I say that, then can I prove that there will be a walk, there will exist a walk of length k from A to B? So basically, what is the proof of this theorem that we have seen in the previous lecture? So let's see the proof now. First, we will prove for m power 1, then I will prove for m power 2, then with induction, you can prove for m power k. Okay, yes or no? Remember, our target is to prove for m power k. But first, I will prove for m power 1, then I will prove for m power 2. Then by induction, you can prove for any m power 2, m power 3, m power 4, any m power k. Yes or no? So let's see for m power 1. That is trivial. For m power 1, the proof is trivial. What is the reason? Because what is m power 1? That is same as m. Okay. So you already know m power 1 represents walk of length 1. M power 1 represents walk of length 1. Okay. So you can see in the graph, if you have walk of length 1 from A to B, if there is walk of length 1, walk of length 1 means what? Just tell me a simple point. From A to B, if there is a walk of length 1, or from A to A, if there is a walk of length 1, what is the meaning of walk of length 1? Can anyone tell me? Anyone want to tell me what is the meaning of walk of length 1? That is simply as directed as, yes or no? As in the graph. That is simply as in the diagram of R. Do you agree? Walk of length 1, that is simply the as, directed as in the diagram of R. Okay. Here you have walk of length 1, here you have walk of length 1. This is same as there is self loop, that is also as. Okay, that is also as, and this is also as. And we already know that m power 1 is same as m. So of course m captures the edges. Yes or no? We already know that m captures the edges. M captures the edges of diagram of R. Okay. And you already know that age means walk of length 1. Okay. What is age? What is age? Age is basically age in diagram of R. What is that? That is basically walk of length 1. Okay. So that's it. This is trivial. Do you agree with me? This is trivial, that m power 1 represents existence of walk of length 1. Okay, what is the proof? The proof is trivial because m power 1 is same as m. And walk of length 1, that simply means age. In the graph representation, every age, that is basically walk of length 1. Walk of length 1 is basically age. So age is walk of length 1. Walk of length 1 is age. Okay, this self loop, this is also walk of length 1. Or I can say this is also age in the graph. This is also age, or I can say this is walk of length 1. So remember, walk of length 1 is same as age. Age is same as walk of length 1. We already know that m will capture the edges. So m is capturing the walk of length 1. Yes or no? M is capturing the existence of walk of length 1. So this is trivial, this is very easy. Now the interesting part is m power 2. If I can prove for m power 2, then with induction you can prove for m power 3, m power 4, m power 5, yes or no? M power 1 was trivial. If I can prove for m power 2, then we can stop and we can say that okay, by induction m power 3, m power 4, m power 5, that also we can prove. Okay, so our task is that let's prove for m power 2. Okay, so what I need to prove? I need to prove that m power 2 represents existence of walk of length 2. What it means? It means that in m power 2 this AB entry will be 1 if and only if there is a walk of length 2 from A to B. Now how to prove it? For m power 2, how can I prove it? Means m power 2 represents existence of walk of length 2. How can I prove it? So in the proof there will be two directions, because remember this is if and only if. This is if and only if. There are two directions here. Okay. I need to prove this direction also. I need to prove this direction also. Okay. What it means? It means that I need to prove two things. The two things are like this. You can see we need to prove two directions. The first direction is if there is a two length walk, means the first direction is like this. If this is given, then I need to prove this. This is one direction. Another direction is if this is given, then I need to prove this. Okay. So you can see we need to prove 1 comma 2. What is 1? 1 is saying if there is a two length walk from I to K, from vertex I to vertex K, if there is two length walk, then the IK entry will be 1. Okay, then IK entry will be 1. This is what I need to prove. Also, I need to prove the reverse direction. What it means? It means that if IK entry is 1, then I need to guarantee that there is some walk, there exists a walk of length 2 from I to K. Okay, so let's prove both of these one by one. The proof is very beautiful. Of course, it's not important for the gate exam. You can skip it, but the proof is easy. Okay, so let me explain. So let me explain the first proof, means the first part, the one direction, the first direction. So I want to prove that I want to prove that if there is a two length walk from I to K, then IK entry will be 1. Okay. Tell me, if there is a two length walk from I to K, then what are the possibilities? The possibilities are like this, that okay, from I to K, there is a two length walk. Okay. So, for example, let's see two length walk possibilities. You just tell me what are the possibilities where two length walks, two length walks from A to B, from A to B. Okay, tell me what are the possible two length walks from A to B? Maybe like this, that from A to C then to B. This is two length walk. Or maybe like this, that from A to A, then from A to B. Or maybe like this, from A to B, then from B to B. Do you agree that these are the possible two length walks from A to B? Okay, yes or no? Now the point is, these three I can capture by a single statement that okay, from I to K. Okay, so from I to K, it's like this, that you have I, you have K, two length walk, two length walk. Okay, let me put J here. Let me put J here. Remember, this J can be same as I, this J can be same as K, or this J can be different. Okay, like here. So you can see this J can be same as I, this J can be same as K, or this J can be different. Okay, is this clear? So now we are discussing, you can see these are the possible two length walks from A to B. To capture all these three possibilities, I can just write like this, that from I to K, there is two length walk. From I to K, there is a two length walk. Means there is a J. There is a J here. Now this J, this may be same as I. Okay, this J may be anything. This J may be anything, remember. What it means? It may be I, or it may be K, or it may be else. Okay, other, or something else. Okay, clear? So very simple. Now, the the statement is saying that if you already have this type of two length walk, then can you guarantee that ik entry will be 1 in m power 2? This two length walk is already there. This is two length walk from I to k. This is two length walk from I to k. Okay. Now, if there is a two length walk from I to k, then can you guarantee that in m power 2 ik entry will be 1? Now let's focus on m power 2. Okay, I will focus on m power 2 now. How to find m power 2? What is m power 2? That is m into m. Okay, so that is like this, m multiplied by m. Okay, now you notice m multiplied by m. Now already there is a walk from I to k of length 2. Okay, this is already given to us that from I to k there is a walk of length 2. Okay, so you can see this will be captured by m. Do you agree with me? This is m. Okay, this is m. This is m. We are multiplying. M power 2 means m into m. So you can see this I to j, this I, this j. Okay, so here I can put 1 because there is a age from I to j. Okay, so I can put a 1 here. Notice there is a age from j to k also. Okay, from j to k also, j to k also there is a age. Okay, so I will put like this. Now when I multiply, what I will get? I will get m power 2. When I multiply, then I will get m power 2. When I multiply m comma m, then I will get m power 2. In m power 2, you tell me what will be ik entry. I want to see what is the ik entry in m power 2. This is I, this is k. What will be this ik entry? Notice one thing. For this ik entry, ith row and kth column will multiply. Do you agree with me? Yes or no? For this ik entry, if you remember, a small point, if you remember from the matrix multiplication, okay, just let me tell you, and from the matrix multiplication, remember, if there is a matrix, okay, if there is a matrix m and if there is another matrix m, okay, then you can see if you multiply them, okay, then here this is m power 2. Okay, now if you just focus on this entry like ik entry, okay, or maybe like ij entry or ik entry, whatever, if this is I, this is k, then what will be this entry? This entry. Okay, so basically I am asking this entry. So remember, for this entry, what will happen? Who will multiply? Ith row here, this ith row, it will multiply with kth column here. Okay, then you will get this ik entry. Okay, and here also remember this I1, this element. Okay, this element is, you can see, let me, you can see that this I1 element will multiply with 1k. Okay, this I2 element will multiply with 2k. Okay, this I3 element will multiply with 3k. Correct? Okay, this element will multiply with this. Okay, it's like this. For example, it's like this, that it's like this is I1 element. Okay, this is I1 element. It is multiplying with 1k element. Okay, you can notice this is like I2 element. This is multiplying with 2k element. Okay, next you can see this is I3 element. This will multiply with 3k element. Okay, and at the end you can see that this is, if you have n elements, then it is in element and it will multiply with nk element. Okay, yes or no? And then you will add them. Then you will get this ik entry in m power 2. This you already know. Okay, matrix multiplication. This is simply matrix multiplication that you study in the linear algebra. Okay, so this is just matrix multiplication concept revision. Okay, so here let's come back to our point. So you tell me what will be this ik entry? This ik entry means this row will multiply with this column, ith row will multiply with kth column. Agree? Ith row multiplying with kth column. Okay, now notice this first element will multiply with this first element, this second element will multiply with this second element. So you tell me, what element is this? This is jth element, yes or no? This is first element, second element, third element, and so on. This is basically jth element. Can I say this is like ij? Yes or no? This is ij. Okay. Now you tell me, like this is first element, this is second element. You tell me what is this element? This one. What is this element? You can say this is a jk. Okay, yes or no? And you can easily see that ij will multiply with jk, this one will multiply with one, that will be one. Then you, if you add 1 plus anything, that will be 1. So can I guarantee that it will be 1? Yes. Okay, it will be guaranteed to be 1. Did you understand? Please tell me. Very simple. It's nothing. You can just take your copy pen and you can just easily see that. See, this entry is basically ij, and here this entry is basically jk. So of course they will multiply one with one with one, this one with this one. 1 into 1, that will be 1. 1 plus 0, 1 plus 0 plus anything, or I can say 1 plus anything. 1 plus 1 or 1 plus 0, basically 1 plus anything. In the Boolean arithmetic, because here we will perform the Boolean arithmetic. So 1 plus 1, that is 1. 1 plus 0, that is 1. In the Boolean arithmetic. So finally I will get 1 here. Okay, finally I will get 1 here. So hence proved that if there is a two length walk from I to k, then in m power 2 the ik entry will be 1. In m power 2, the ik entry will be 1. Hence proved. So one direction we have proven. Now let's see the another direction. The another direction is like this, that in m power 2, if ik entry is 1, then can you prove that from I to k there will exist a walk of length 2? Okay, this is also very easy to prove. The question is saying that m power 2, in m power 2 ik entry is already 1. Okay, what is m power 2? In m power 2, the question is saying that ik entry is already 1. Ik entry is given to you as 1. Ik entry that is given to you as 1. Now what can you say about, what can you guarantee that from I to k there will be a two length walk? Can you guarantee? Yes, I can guarantee. Remember, how can I guarantee? Because in m power 2, this ik entry is 1. What is m power 2? How did we get m power 2? M power 2 was basically m into m. Okay, m into m. That means m multiplied by m. Okay, and you can see that this ik entry is 1. But how are we getting this ik entry? For that, this ith row will multiply with this kth column. Do you agree? In m power 2, we are getting this ik entry 1. But how are we getting this ik entry? To get this ik entry in m power 2, we need to multiply ith row of m with kth column of m. Yes or no? This is also m, this is also m. So ith row of m I need to multiply with kth column of m. Okay. This entry is already 1. What it simply means, remember, this I1 will multiply with 1k. This is 1k and this is I1. Also notice, this is I2 and this is 2k. 2k will multiply with, see, I2 will multiply with 2k. I1 will multiply with 1k. Yes or no? Let me tell you more. For example, this is I3 and this is 3k. Okay, and so on and so on. Can you give me a general case? Can you give me a general case? The general case will be something like this, that this is I, and let's assume this is a some, for example, j. Okay, ij. Then what is this? This is a jk. Ij will multiply with jk. Remember, very simple point. I1 will multiply with 1k. I2 will multiply with 2k, I3 will multiply with 3k, Ij will multiply with jk. Yes or no? Now, if this ik entry is 1, then somewhere it is happening that 1 is multiplying with 1. Do you agree with me? If this ik entry is 1 in m power 2, if this ik entry is 1 in m power 2, to get this ik entry, we need to multiply ith row of m with kth column of m. Now you can see, to get this 1, somewhere 1 is multiplying with 1, because if 0 multiplies with 0, that will be 0. 0 multiplied by 1, that will be 0. 1 multiplied with 0, that will be 0. Now, if this entry is already 1, it simply means that somewhere 1 is multiplying with 1. Do you agree? Means that somewhere it is happening that 1 is multiplying with 1. Then only this entry can be 1. There is a guarantee that somewhere 1 multiplies with 1. Somewhere. Okay? Means one of these element is 1 and that is multiplying with 1. But remember, ij will multiply with jk. I3 will multiply with 3k, I2 will multiply with 2k, I1 will multiply with 1k. Somewhere 1 is multiplying with 1. Then it means this type of possibility, this type of situation is we are getting. It means that we are getting this type of situation that ij is 1, okay, and jk is 1. Okay, yes or no? Remember, this j can be anything from 1 to n. Here, j can be, here j can be anything from 1 to n. Okay, but the point is, definitely this type of situation we are getting, that 1 is multiplying with 1, then only we can get this entry 1. Okay, this ik entry I want 1, so it simply means that somewhere 1 multiplies with 1. Then you know that 1 or anything, that will be 1. Okay, so somewhere this type of situation is creating. Yes or no for some j, and this j can be anything from 1 to n. So finally you can see that ij is 1, means from I to j there is a age. Ij is 1, ij is 1, it means what? Ij is 1, it means from I to j there is a age. Jk is 1, it means what? That from j to k there is a age. That's it. That's it. We got a two length walk from I to k. We got two length walk from I to k. That's it. Hence proved. Hence proved we got two length walk from I to k. We got two length walk from I to k. Okay. Hence proved. That's it. So finally we have proven both the directions. Okay. And our proof is over. Okay. Is this clear? So we have proven for m power 2. Both the directions we have proven. This direction also, this direction also. Okay. For m power 2, you can see. For m power 2, this direction as well as this direction, both the directions we have proven. Okay, so this also we have proven, this also we have proven. So finally I can say that for m power 2 we have proven the theorem. Now remember, for m power 3, m power 4, m power k, you can just use the induction. We will not do that, but you already have the idea. You know what is proved by induction, but the point is that you can just use the induction, and by induction you can prove for m power 3, for m power 4, m power 5, m power 6, and so on. Okay, that we will not do, because my target was to just explain the proof for m power 2. That is interesting, m power 2, both the directions we are proving. So for m power 2 we have seen both the direction. Now m power 3, m power 4, m power 5, that is a boring proof, proved by induction. Okay, just you can do it if you want, otherwise you can skip it. We are not going to do it, but I have shown you, the meaning of m power 2, the proof of m power 2, and by induction you can prove for m power k. Okay, that's it. This is our chapter. We have seen everything in the relation closure. We have seen the concept of relations closures, reflexive closure, transitive closure, symmetric closure, anti-symmetric closure, irreflexive closure, different types of closures. Then we have seen If matrix representation is given, graph representation is given, set representation is given, then how to find various type of closures? Then we have seen power of adjacency matrix of a relation. We have seen the concept of walk, length of a walk. Okay, we have seen that if M is the adjacency matrix of a relation R, then what M power K signifies? What is the meaning? What are the significance of M power K? We have seen what is M power 0, that is identity matrix. Whatever relation you take, M power 0, that is always identity matrix. So all these concepts we have seen. Then we have seen commutativity of relation closures. Two different type of closures. Are they commutative? Are they not commutative? We have seen very important point that transitive closure, symmetric closure, they are not commutative. Okay, but remember, reflexive closure, symmetric closure, they are commutative. Also, reflexive closure, transitive closure, they are commutative. Then we have seen equivalence closure of relations. How to find equivalence closure of relations, that we have seen. Some very good questions we have done. Okay, and then we have seen the proof, this optional proof, okay, related to power of adjacency matrix of a relation. So everything we have seen, with proof we have seen, with a lot of practice, and all the gate PYQs we have done. Okay, we have seen Varsal algorithm also. The introduction to Varsal algorithm we have seen. Okay, so we have seen the time complexity. All these concepts we have already studied. Okay, now in the future gate exam, whatever question comes from relation closures, you can easily solve it. I have full confidence on you because I have covered each and everything that is there to be covered. Okay, with practice, with gate PYQs, with proof, in depth, everything we have covered. Okay, so thank you everyone. This is our chapter is over. The chapter was relations closures. Okay, so thank you everyone. Please share your feedback. Please like this session, and please share your feedback with me. Did you like all these lectures? Did you understand all these concepts? So please share your feedback with me. Okay, thank you everyone.